Hello, everyone. This is the results of my research that I started last summer on constraining black hole mass and charge from shadow and inner shadow morphology. Just as an introduction, some background information. The first target of the Event Horizon Telescope, M87 star, has a diameter in the sky of about 40 microarc seconds, whereas the EHT has a theoretical limiting resolution of 25 microarc seconds. And excitingly, the BEX mission plans to increase this resolution to about 6 microarc seconds. And so at these resolving scales, we'll be able to resolve a few key image features that we haven't before, and we'll be able to do some cool science with that. So what can we see at higher resolution? Well, the two key image features that I want to focus on are the inner shadow and the photon ring. So as some background information, the inner shadow actually refers to everything interior to the lensed image of the horizon, the event horizon of the black hole. So it's actually a region interior, whereas the photon ring is a uh, ring of light seen at a very specific radius. Um, and I'll go into a little bit about how that comes about. This model that we see here is actually of a typical Kerr black hole with angular momentum. My research focuses on the Reissner-Nordstrom case, so a black hole with electric charge instead of momentum. And the reason that we attempted to model in this way is because it is a little bit easier to model computationally, being spherically symmetric. And a lot of the conclusions that we can draw from this space-time metric is actually applicable to the Kerr case as well. So if you can look to the left here, we have a cross-section of a 3D black hole space-time. And we have some rays that are originating from a flat accretion disk and that are actually converging towards a bound orbit at this radius, the red dash circle, before looping around and then zooming off towards infinity. So this radius that all of these rays seem to converge at is called the critical curve radius. Um, and it's at this radius that we can find the photon ring. So in 3D space, it is at about a radius of 3 gravitational units. And yeah, if we look over to the right here, we have some plots that are actually the image in the image domain. So this is what an observer would see if we go out to infinity and gaze at a black hole. So in this case, our red dashed line is still our critical curve radius, but it has been lensed out to a radius of about 5.2 gravitational units. And this radius actually corresponds to the impact parameter in our 3D ray tracing model on the left. So that is the red dashed line, the location of the critical curve and where the photon ring will appear. The solid orange circle is the lensed image of the horizon of the black hole, and I've left a solid black circle to represent the original size of the event horizon. So anything interior to that orange circle is considered the inner shadow. So in these diagrams, I have displayed how the image of the lens horizon will change based on viewing inclination. That is the theta s parameter. And that just describes if there is a tilt. So a viewing inclination of 0 means that every point along the accretion disk is equally distant from the observer. Whereas when we have some viewing inclination, there is going to be a tilt towards us. So in this case, in the 20 degrees case, the bottom is tilted towards the observer, and so we have kind of a squishing on the bottom and a stretching on the top. So these are lensing effects. Now, the C parameter is actually the emission angle, or also referred to as the scale angle. And so something that is a little bit inaccurate about the diagram on the left is that it assumes a completely flat accretion disk, whereas a more accurate representation of it would be two cones kind of extending from the center of the black hole. And thus, any radiation that is originating from the accretion disk that has some distance away from the center will actually not originate perfectly from um, the equatorial plane of this black hole. As such, uh, the rays are actually going to originate from a little bit further up, some height above the equatorial plane, and thus originate a little bit closer. And this can actually cause its own lensing effects and shrink the shape of the lensed horizon. So as we can see, the top right case versus the bottom left case of these black hole models, we see the lens horizon has actually been squished a little bit. And then on the bottom right, I have an extreme case, a nearly edge-on case of a viewing inclination of 80 degrees, just so we can see how extreme the lensing of the inner shadow can get. Now, in all of these cases, you'll notice that the red dashed line, our critical curve, has remained the same. And this tells us that it is actually unaffected by viewing inclination or emission angle. So what are some things that we know about the inner shadow? We know that its asymmetry follows a specific curve depending on the inclination, and that this curve is unchanged at different charges. Um, Whereas with the average radius, and we're using average radius because of this asymmetry, it is actually dependent on both the inclination and the charge of the black hole, as we can see on the right. So what can we do with this information? Well, first I began with a contour map across these two parameter spaces. So we have charge and inclination on the left, and then charge and emission angle on the right. Um, and yes, we just drew isoradial contours along this parameter space to see, for example, a radius of 10 along that line, um, each parameter that produces such a radius. So what can we actually do with this? Well, we can use these contour maps in order to constrain black hole parameters. So given an observation of a black hole with some resolution, assuming a very high resolution, and we have two independent measurements of the lensed horizon radius and the critical curve of the photon ring radius, we can place those isoradial curves onto our parameter space. So in both of these cases, we have curves for the lensed horizon. And in the case of inclination and emission angle, as I explained before, the photon ring is actually, the radius is unimpacted by these two parameters. So the line that represents a charge of zero point 0.2 is actually going to represent the isoradial curve of our critical curve radius that we found. So where these two lines intersect is going to constrain the parameters that produce the actual physical image that we are seeing. So as we can see on the left, the two lines cross at a charge of zero point 0.2, which we expect because of the critical curve, and an inclination of about 20 degrees. I include a 1% uncertainty in the inclination case, and then I also include a 5% uncertainty as well in the emission angle case. And what these uncertainties will tell us is that in the case of not super fine resolution, we at least still have a region of possible parameters, which is better than nothing. Now, in the case of charge and mass to distance ratio, mass to distance ratio is something that will impact our perceived photon ring radius. And such, we have two contour maps. On the left here, we have the inner shadow radii, and on the right, we have the photon ring radii. And so similarly, we can constrain the real physical parameters that produced both of these observations. And as we can see, they converge at a value of charge of 0 0.2 and a mass distance ratio of 3.78. And in the case of the 1% uncertainty, we have a skinny region, and the 5% uncertainty, we have a little bit of a larger region, but it does constrain it compared to the entire parameter space. Now, something very specific that my research wanted to analyze was the case of emission coming from some emission angle that is not the equatorial plane, and what might happen. So in that case, if we were to have emission from some height above the equatorial plane, but we are fitting, assuming that our emission is coming from the equatorial plane, then we have a plot like this, where our horizon curve has actually been shifted to the right. And in the case of super high resolution, we actually have an inconclusive result because these lines do not intersect. The same is the case for 1% uncertainty. And for our 5% uncertainty, we do have an overlapping region, but it has been translated to the right of where we expect our parameters to be. So, a key conclusion of my research is that when we are trying to constrain these parameters, but we are assuming um, radiation is coming from the equatorial plane, we can actually gain inconclusive or just a false result region. So, this is something we want to keep in mind when we're using BECS for these high resolution um, observations. And yeah, that's the extent of my research. Thank you. And is there any questions?
Thanks a lot, Julian. This is really great work.
Thank you.
Any questions? Alex?
Yeah, this is really, really great. So in the course of doing this work, have you come up with some ideas that you're excited to think next, to think about next? Where do you see yourself taking this now?
Well, I definitely there is some things I want to work on. So I would like to kind of have a more in-depth idea of the degeneracies that arise among these different parameter spaces. So like charge, inclination, um, emission angle, these all just change our average radius measurements. So there's kind of a lot of different degeneracies to consider. And I'd like to map out kind of regions where we have a higher concentration of, um, I guess, degenerate parameters. So that's something that I'm working on. I guess that would just be helpful to see like, okay, well, we have to consider XYZ as uh yeah, potential sources of degeneracy for our measurements. And so that's kind of what I'm thinking of next.